and computing, we increase dramatically the complexity of an already complex system. Right? And complexity and robustness not necessarily go together. The third part is by introducing an information and communication infrastructure into the grid, we increase the vulnerabilities. Okay? We cannot enforce any more security by obfuscation, but as we integrate general purpose networks like the internet into the power grid, then we expose the power grid to all the attacks that can occur over a communication network. Now it's time for you to give your contribution to this list. So if you guys want to add something or remove something, please, you can.
On their reliability.
Reliability. Okay, let's do that right now. So you don't think that's a? I guess it's a little different from safety. Okay, fine.
Yes, definitely different. And the other one is speed of response. You're going to be able to recover from a out condition much faster.
Okay, safety doesn't cut it, no.
No, safety is different than security. And safety just means that when you send out the workers, they're not going to get electrocuted.
Okay, so I had a broader view of safety, but okay, so let's put, so what is speed of response? Okay. Okay, sounds good. Anything else? I need some cons here. You guys are two pros. Or privacy issues as well. Privacy, thank you. Beautiful. Yeah, okay, thank you. All right, anything else? All right, good. This is keeps increasing. I'll let you know in a year what happens. Okay, so let me now talk about cyber-physical system. This is a word that has emerged in the past few years, and in my view, it refers to the convergence of different domains. I'm going to list what I think are the three major domains. It's control, communication, and computing. So cyber-physical systems are the ones that are at the intersection of these three domains. It is a challenging, there's lots of challenges. I think the first that I foresee is that these domains have developed in a parallel way, in some sense. So they have different languages, different methodologies. So bridging them, I think it's already a challenge. So sitting three people from three different fields and speaking the same language is already a big challenge. Therefore, developing a science of cyber-physical security, I think, is a major challenge. So there's a question that needs to be answered because many times we invent new words for old concepts. So it's really cyber-physical systems are really the emperor's new clothes. And you can argue that we have designed cyber-physical systems for decades now. Whenever there's a digital controller into a control system, that's a CPS, right? Whenever you took your undergraduate control lab and you were controlling the inverted pendulum, that was a cyber-physical system. You have a physical system, you have sensors, you have communication, which is usually a serial communication to a computer. Computer then computes the control input and then sends the control input through, again, another communication channel to the controller. So why didn't we care about CPS back then? So what is different, I think, there was separation of concerns. So we designed our communication system in such a way that we made sure that he had enough bandwidth to carry on the traffic that it did. We designed our computing system in such a way that it could compute the control input in time to be delivered to the actuator. So in some sense, there was really no coupling between these different domains. A control engineer could safely abstract away the computing and could abstract away the communication and design his controller as if these two subsystems did not exist. Okay, and there was no notion of sensitivity, right? The specs were perfectly matched, so the control performance was not sensitive to the particular performance of the communication of the computing. I argue that in large-scale infrastructure, this is not the case anymore, and the reason is that we cannot afford to build dedicated computing and communication infrastructure for each resource that it needs. We are going to have to rely on distributed computing. Cloud computing is emerging, for instance, and it is a manifestation of it. And also, we have to rely upon a packet-based network, which are going to be used and carry on traffic for different applications. So my claim is that these three assumptions we cannot do without the separation of concerns, lack of coupling, and sensitivity. And therefore, when we design, we have to co-design. Okay? And I think the smart grid are a prime example of CPS. Okay, so I'm going to focus on the among all the issues that have to do with cyber-physical system. Let me try to narrow my focus on the deal of security, on the issue of security. So in information security, we have three major properties that we want to satisfy. And we have confidentiality, integrity, and availability. Okay. So for cyber-physical systems, especially for these systems that use information and communication infrastructure to support its operation, what we really want to enforce is the reliability of system operation, right? And so the goal is somehow different. So the rebooting is not an issue in cyber-physical system. Think about the power grid. You don't turn down the power grid to troubleshoot an attack on it, for instance. Same thing if you're flying on an airplane and there is an attack on the entertainment system, right? You don't turn off all the engines and the whole system. You need to keep flying. Okay? So continuity of operation is essential to it. So also, what are the scope of an attacker in CPS? And here I'm just putting a probably non-exhaustive list of them. So for instance, somebody might be interested in disrupting operation or destabilize the system, right? Take the Stuxnet example. I'm going to go back to Stuxnet later on. So another reason could be reduced system performance. Right? If you have a competitor and you want to gain an unfair competitive edge, you might introduce a very dull attack, which all that it does just decreases the performance in the operation of your competitor, so that decreases its competitivity. Okay, there's financial gain, which can go from shifting all my consumption to my neighbors so that I don't pay my electric bill, to rigging the electricity market so that I can take advantage of buying and selling electricity. And so there's different contexts like cyber warfare, so intelligence or counterintelligence, depending on your point of view. Commercial advantage or just criminal intent. And we have observed some examples of this, and many more we are not observing just because they're not known to us. So what are the type of attacks on on cyber physical systems. So all the cyber range of attacks is applicable, right? We're using a ICT infrastructure to support the physical infrastructure. Therefore, we are going to experience all the range of attacks that we would on a regular cyber system. There's physical attacks that can occur, that can go from destruction of physical asset to manipulation of them, and they usually have to do with tampering. Think about a short-circuiting a smart meter so it doesn't measure any consumption, or think about building applications, just corrupting the measurement of a thermometer by putting a microclimate around it and have it measure a different temperature than what the temperature in a room would be. That would attack the integrity of the sensor without actually corrupting the cyber side of the system. And I think a big threat is the one of insider attacks. Think about the smart grids, thousands and thousands of operators, and in the grid so there's a high chance that somebody might be disgruntled or might be just bribed, and an insider is an authenticated user, so it bypasses all the cybersecurity defense that a system might have. In terms of remediation, I think so. There's detection and isolation. Again, we want to guarantee continuity of operation. And by doing so, we do so by guaranteeing graceful degradation of performance. We do not abruptly turn off a system, right? We want to keep operating, and we can, I think we can deal with less performance. For instance, islanding could be one solution in power grids. And ultimately, we want to restore complete functionality of the system. Okay, so this is the overarching introduction to my talk. So I want to now get a little more specific, get more into the technical issues. So I want to provide some insights via case studies to try to motivate what are the kind of problems that might arise when we attack a control system. Okay. So I'm going to focus, I'm trying to scale down. I'm not going to talk just about smart grids. I think there are more basic problems that we need to face before going to this large scale. So I'm going to focus on control systems. I'm going to define what control system I'm going to deal with. And then I am going to talk about attacks on sensors. Okay, and in particular, I'm going to focus on two types of attack, something that I call sensor replay attacks, and you will see that this is more familiar than you think to you, and then integrity attacks on the sensors, where you just change the sensor data, and provide some results, which I hope will gauge your curiosity and your interest as well. So I'm going to assume a centralized system. For now, we have several results for distributed control systems, but there was no way that I could fit it within the time constraints of this talk. So if you have question about it, I'll be happy to talk to you after the talk or later in the afternoon. And then I'm going to give some motivating and mostly academic examples to try to explain or provide intuition behind these results. Okay, so let me provide. I don't know how many have background in control or system theory, at least linear system theory. Okay, so we have a few. So let me try to make it as simple as I can. So X is the state of the system. Okay, in power grids it could be the phase, the voltage, for instance, which evolves according to a differential equation. For a discrete time system, it evolves according to a difference equation. And we assume that this system is linear and we don't know it precisely. So WK will model uncertainty about our model. Engineering model is always a less than perfect description of the physical system. Sensors are used to monitor the system. And so YK is a vector which contains all the measurements of the system at time k, and it is a function of the state, okay, plus some observation noise, okay? This is the standard linear Gaussian model. Okay, so each element in the vector yk represent the reading of a sensor at time k. Okay. Just to give you an example, and I will go over it later on, take a vehicle moving on that's the simplest system I could think of, on the x-axis, right? So x dot will be its velocity, and x will be its position, right? And it will follow some dynamical equation which describe the evolution of the position and of the velocity of the system on this straight line. Okay, and again, these are the discretized equation of the unicycle model, or even simpler than the unicycle model. So, and for instance, we could use several sensors. In this case, let's consider two sensors. One is the velocity. We measure directly velocity with some noise, or we can measure, this would be a tachometer, or we can measure position through a GPS, for instance, with some noise. So let's equip our control systems with tools that usually control system engineers adopt. So the first one we'll call a filter or an estimator. So given the observations or the sensor data, we want to reconstruct here the state at each time, given all the observations up to that time. So that's what this notation means. This is an estimate of the state xk at time k plus 1, given all the information, all the observation up to that time. Okay, the system is also equipped with a closed-loop controller. Here, this is an implementation of so-called LQG controller. It's an optimal controller that tries to regulate the system around a point. Okay, so it penalizes the perturbation of the system around this equilibrium point with using as little energy as possible. So this is the functional that is trying to minimize. The solution is a textbook solution, which is in the infinite horizon at least. It's a linear controller. It's a linear function of my estimate, and it's static. Okay? This is even more sophisticated than what people usually use. The third component of my control system, it's called a failure detector, or which is used to detect abnormalities, anomalies in the system. The way it works, and this is the basis for it, is it triggers an alarm if a certain condition is satisfied. So you build a function, gk, which you compute at each time, and you set a threshold, which, if you go on textbook on detection, then you can design depending on your desired probability of false alarm. Okay, so you compute this function, which is usually a function of all my observation and the knowledge of the system that I have, of the model. And so if the value of this function is above the threshold, then I raise an alarm. There is a discrepancy between what I measure and what I expect to measure. One implementation, and the one that is mostly used in practice, is this chi-square detector, which this function is based upon the difference about what I measure at time k and what my model tells me that I should be measuring at that time. Okay, so if and I create a quadratic function of it, which I weigh against the observation noise, basically, and if this function is larger than a certain threshold, then I raise an alarm. Okay, so this is the system. Let's go over the first attack that we conceived. So that was in the Great Allerton Conference, which I always enjoy. I think it was the first cyber-physical system conference. It's in its 50th year. If you look at the title, it's Control Communication. conference. Let's take this attack model, okay? So this was, we published this in September 2009 in Unsuspicious Times. So the attacker can record and modify sensor readings, and while it injects malicious control input into the system. Okay. So how the attack will work, so assume that the system is in steady state. Okay? If you're controlling well a system, that's where you want to be. Okay? That's where you minimize your performance index. Okay? So a system that performs really well is going to be in that state. So what I'm going to do is record a sufficient number of observations without adding any control input. And then what I'm going to do, I'm going to inject malicious control input into the system while I'm replaying the old observations. Okay? So when I do this, basically I cut the umbilical cord or the feedback loop, and therefore my controller doesn't have any information anymore about the system. So the only hope that I have in order to counter this attack is actually to detect it. Okay? So does this remind you of anything? So this is our abstract at the Allerton conference. So we assume the wish is to disrupt the operation of a control system in steady state. And in order to inject an exogenous control input without being detected, the attacker will hijack the sensor, observe and record the readings for an amount of time, and repeat them afterwards while carrying out its attack. This is a very common natural attack, like in movies. I should call this the Ocean's 11 attack, for instance. It would probably make the case. And people ask me, so what do? You just eat too heavy at night, and then you have bad dreams, so you dream about attacks, and the next day you write a paper. I said, yeah, that's basically what I did, aside from watching lots of movies. And so some people were a bit critical, and until 6 months later, I read in the New York Times, the worm itself now appears to have included two major components. One, I have nothing to do with it, which is how to break into the system. That was very sophisticated. And one was designed to send Iran's nuclear centrifuges spinning wildly out of control, inject exogenous inputs. And the other one seems right out of the movies. Computer programs secretly recorded what normal operations would look like, and then played those readings back to the plant operators, like a pre-recorded security tape in bank heist, Ocean's 11 again. Okay, so I got my revenge. Two disclaimers. I had nothing to do with this. And second, if you know somebody who did, please let me know, because I would like to collect royalties on this attack. Although I have some there were beautiful stories on who would do it and why, and they put observations and watermarks into the code. But anyway, so this attack was real, and it was quite natural if you think about it. That's what you would do, and that's why people in movies use it all the time. Okay, finally, after getting my kicks out of this, let's go into the details of it. So you have the system and the estimator that we described, the controller that we described, and the detector that we described. And this is the attacker that will hijack the sensor. Replay yk prime refers to the replayed data, while yk is the real data. And then it would inject an input into the system. Forget about the input. It doesn't matter. We are now concerned about detecting the attack. So what happens, first of all? Let's do some example. Let's play with this attack, and let's see how the detector behaves, right? So we run some examples. This is one of them on a simple scalar system. And what we notice is that for some system, this chi-square detector cannot distinguish the system under replay from the system without replay. If you look at this graph, it shows the detection rate or probability versus time, and it's a meager 5%, which is exactly the false alarm rate that we had set for the system, which means that this detector will not be able to detect this attack. So the reason is, if you remember, this detector was based on this difference, which we call the innovation in control system, right? The difference between what I measure and what I expect to measure. And if you look at how it evolves under attack, this is the innovation under attack, is exactly the innovation without the attack, the t is a shifting in time, right? This is the innovation without the replay attack, plus this term, which evolves according to this matrix A. And and it depends on the difference in initial condition. This is a technical thing that you can live without. So basically, if this matrix A is stable, meaning he has all the eigenvalues within the unit circle, this term will go to 0, which means that after a little time, very quickly, the innovation under replay will be equal to the innovation without replay, and that's why you will not be able to detect that attack. Okay? So look, this matrix depends upon the closed loop system. So L is the gain of my controller, and K is the gain of my estimator. So it really depends upon my design. If by design I make this matrix unstable, then I will be able to detect this attack. But let's say that we design this system for performance, so we don't care about the stability of this metric, and then we come up with this A. So if A is unstable, we are fine. If A is stable, what should we do? Do you have any suggestion? Why is this attack successful? Think about the movies. Huh? Everything looks okay, exactly. If in a movie there was somebody who every once in a while would wave his hand in front of a camera, right, you would understand right away whether there's a replay of all scenes or not, right, as long as this is done randomly. So it is really the fact that the system, as you correctly pointed out, is in steady state that allows this attack. So what we propose is, what if we perturb the system physically? Right? Then, if we add a random control input, if the system responds to this input, then my sensors are actually doing their job. If it doesn't, then there is a problem with my sensor. So, in other words, we are these random control inputs act like timestamps. What we are really doing is authenticating the sensor, not in the cyber way, in the common way, but through the physics of the system. Okay? And I think that is a interesting architectural suggestion for cyber physical systems. As you know, we can attack a cyber system remotely by being anywhere, but really, if there is a physical channel that we use to authenticate components, then attacking it is actually more difficult, right? So are we paying something for this? Of course we are. We are perturbing the system. Therefore, performance, we lose performance. First of all, because if we want to keep the temperature in this room at 75, introduce a performance, then the temperature is going to start oscillating. And if we take that performance index, which wants as accurate control as possible, then there's a penalty that goes into there. And also we introduce energy into the system, right? And if we want to penalize the use of energy into the system, that's another penalty into our performance. So the controller that we had designed is not optimal anymore when we introduce this perturbation. So we take our controller, which is defined for performance, and we add this control input to it. Okay, the way we make it Gaussian, okay, and we make it with zero mean, because we don't want to introduce a bias into the system. Okay, so let's say that this perturbation is IID with zero mean and with a certain covariance. Right? The higher the covariance, the more we perturb the system around its desired operating point. Okay? So the first thing that we see is that the control cost increases. That means that our performance decreases. And for this particular system, this LQG control, we can actually measure it. We can quantify it. And the loss in performance is proportional, linearly proportional with Q. Which, from a qualitative perspective, you would imagine, right? The higher the Q, the more I perturb the system, the more I lose performance. But this is a nice characterization. So the first thing that emerges is that in this case, enforcing security means loss of performance. So a natural trade-off between performance and security starts coming up. Practically in the equation, what happens if we, so this is the innovation under attack. It's again the innovation without the attack plus this term, which we might go to 0, plus a term, an input term, which depends upon the perturbation. Okay, and thanks to this term, we'll be able to distinguish the innovation with replay and the innovation without replay, and therefore detect our attack. Okay, so this is the new system diagram where now we have introduced this physical authentication signal. So let me give you, so in general, you cannot compute detection rates in closed form. Unfortunately, that's one of the shortcomings of detection theory. So let's use some simulation, a very simple simulation, a single state system with one sensor. We pick some parameters, and we set our detector window, and we set our false alarm rate, and with all this information, we can design our estimator, controller, and detector. Okay, so if we do this, then we look at the detection rate. These are just simulations. This is time versus detection rate for different values of Q. Q, remember, was the covariance. Right? At 0 means that we are not introducing any perturbation into the system, and therefore, my detection rate is the same as my false alarm rate, so useless detector. As we start increasing Q, you can see that our detection rate increases as well. So the higher the probability that I want, the more perturbation I have to introduce into the system, and so the more cost of control I incur. Okay, so the take-home message from this is, having a higher detection rate and therefore a higher degree of security incurs a certain cost. And second of all, if you have to be careful not to. This is kind of increasing the gain in your control system. You have to be careful not to render the system unstable. Okay, so this is the first example. Do you have any questions at this point? Be happy to take questions. Okay, so this is just an example. We use the Tennessee-Eastman model, which is one of the few readily available models for a chemical plant. And the example is what you would expect from a chemical plant. You take two reactants and produces a product D. Okay, so this is a nonlinear plant. So it's a real scale nonlinear plant. I'm not sure how many states, inputs and measurements it has, but we applied our technique to this particular system, and I want to show some of the results that in practice you get. So to the left, you see the system where the controller is designed just for performance. So here you have your chi-square detector, right, where you set a threshold at 6 by 10 to the minus 4. So it's very low. It means you're going to have a lot of false alarms. But notwithstanding that, the values are always below this threshold. That means an alarm is never raised, even though at time 15 there is a replay attack that occurs, and therefore there's no detection. So on the right, we've implemented our scheme for detecting this type of attacks, and you see that as the attack occurs at time 15, the function of the detector goes significantly above the threshold right away, and therefore we can raise an alarm just 25 milliseconds after the attack occurs. So in practice, these are very, very effective schemes. And what I want you to notice, I didn't cheat. Actually, I cheated the other way around. Here I put a much higher threshold. Right? This is 0.5. So it's 3 orders of magnitude higher threshold. And notwithstanding that, I can still very easily detect the attack. Okay. So let's shift gear. Let's move to a different type of attack, which is a smarter attack. Okay, let's say the attacker has full knowledge of the system model. So in the previous attack, the attacker only needed to know that the system was in steady state. Okay, he didn't need to know how the system worked accurately. Here we assume that you can consider this an insider, for instance, that knows what are the system dynamics, okay, and what the sensor measurements are. And what it does, instead of just replaying the observation, it corrupts a subset of this observation and injects a bias into this observation. So gamma is just a diagonal matrix which has ones in correspondence of the sensor which are corrupted. Okay? And in correspondence of that, it introduces a bias in the sensor measurement. So, and the attacker wants to affect the system operations, but it doesn't want to be detected. That's the key point. So it wants to attack, but under the radar, under the noise level, perform his attack. And so the questions are, can the attacker successfully destabilize the system with just very mild, imperceptible attacks? So if I can take a poll, do you think it can? Says yes? Okay, we have a few yes. Okay. The rest I assume is no. Okay, you have to vote. And voting is fundamental in democracies. That's what I always tell my students when I want to wake them up from my boring teaching. Needless to say, most of them don't wake up. So if not, I would like to measure what's the extent of the perturbation that I can introduce into the system without being detected. Okay? So this is the attack model, and in the interest of time, let me go a little fast on this. So again, this is the innovation under attack and without the attack, and this is the innovation without under attack, without the attack and under the attack. And I build the difference in, this is basically the difference in my detector function, right? From the case where there's no attack and the case when there is an attack. And I put, again, this threshold. If this threshold is low, it means that my detector under attack will have pretty much the same values as the detector under attack. Therefore, it means that I will not be able to detect this attack. So you can see this alpha as my threshold, right? If I make the difference between the value of the detector under attack and without the attack within this threshold, then it will not raise an alarm. Okay, that's all it's saying. So, let me define this k-reachable region, which is the set of states that the attacker can reach at time k without being detected, so with this attack being feasible. The total reachable region for the attacker, that means where can the attacker steer the system, it can be computed by taking the union at each time of these regions, okay? The infinite union. So the first result is which sensor should I attack or which sensor should I protect? So this is a necessary and sufficient condition for the system. So the reachable region R is unbounded, meaning that I can render my system unstable if and only if these conditions are satisfied. So the A has an unstable eigenvalue, so it has to be open loop unstable. And then this is the most important condition. I believe that this one is a consequence of this, but I haven't proved it yet, so I'm going to put both of them. CV is in the span of gamma. That means that this is the eigenvector corresponding to an unstable eigenvalue. If I multiply it by C, which is my observation matrix, if this has to be in the column space of my attacker, of my attacked sensors, okay? And then V is to be reachable for the dynamical system. So what I'm going to do under the radar, I'm going to move my state toward the unstable eigenvalue, and then I'm going to just let the system go unstable without even noticing it. That's basically what an attacker would do. So this algebraic condition, I think, has a very good intuition. It provides recipes both for the attacker and for the defender. For instance, to check the resilience of the control system, all that you need to do is check with the unstable eigenvalue, look at the eigenvectors, and compute CV, okay? And then therefore, you know what are the sensors that are more critical to protect for the defender and to attack for the attacker. Okay? To improve the resilience of the sensor of the system, then the defender could put redundant sensors or add physical protection to certain sensors. I think this is quite desirable for large-scale infrastructures like smart grids, where protecting all the assets is impossible from a cost perspective. Okay, and the other thing is that says is if this vector CV is sparse, that means that you only need to corrupt a few sensors in order to send the system unstable. Okay, that's what we get out of this mathematical results. So yeah,
is your eigenvector?
Yeah, the eigenvector associated with the unstable eigenvalue. Yeah. Okay. So not all the systems satisfy these properties. For the system that do not, how can you compute the maximum perturbation that you can, and this is a measure, in some sense, indirect measure of the resilience of the system to this attack. So what happens, you have to take these unions of these reachable regions. So as you might expect, you have to do a reachability computation, which cannot be done in closed form, but there exist numerical methods like ellipsoidal computation that you could do in order to satisfy this. And so let's go back to our car or vehicle moving on the straight line, and you have the two sensors. Okay, now, if you had a choice of computing the tachometer or the GPS, which one would you choose? If you're an attacker. Okay. Velocity? A few. Position? You got more? Okay. All right, so I guess you guys had the right intuition. So if you corrupt the position sensor, this is the value of my detection function, so it never exceeds its threshold, so you don't get detected. But the position goes to infinity, meaning that you can move this car along the straight line wherever you want and not be detected. So the position sensor is a good sensor to compromise if you want to induce a very large perturbation into the system. And if we do our reachability computation, this is the upper bound and the lower bound of the reachable region. You see that with iteration it grows, and you will see it eventually goes to infinity. So if you corrupt the velocity sensor, then the effect of the perturbation, so the condition that theorem are not satisfied, so you can only perturb the system in a bounded way, and you do this reachability computation. So the red is a lower bound on the reachable region, and the blue is, as you see, the unions is a union of ellipsoids, is the upper bound. It's actually pretty tight, so the reachable region is somewhere behind, and this is measured at a time k. That's delta ek. Yeah. Okay. So I think I'm running out of time. So we have an application on electricity market pricing. So I'm just going to give you the basic idea. This is a particular case of this integrity attack where the problem is static, it's not even dynamic. And basically we have a scheme by which if you affect the flow measurements on the transmission line, you can affect the real-time pricing in the local markets. And therefore, if you play a strategy where in the a priori, the day ahead, you buy and sell in two different places at different prices, and then the next day you can enforce that these prices on these two transmission lines are the same, then if you bought at a lower price than you're selling, then you make money. Okay, that's the basic strategy, and you can actually use these techniques to do this without being detected. Okay, so just changing slightly the the measurements on these power lines. Of course, pricing is more complicated than that, right? There's lots of other factors, but the human operator have a lot of power in this. So a bribed or not diligent system operator could actually rig, or set of them could rig the market, and all they have to solve is a bunch of optimization problems, and I just don't want to. So this is the strategy for the attacker. Okay, so this is. You want to maximize, you want to make sure that the lines the next day look as uncongested as possible. That is maximization. And you want to make sure that you do not get detected. That's what the constraint has. Okay. This is an example. Okay, so let me just conclude. By saying that, first observation is that surprisingly, there are small attacks that run under the radar can have quite serious consequences on the operation of the system. I am preaching to the choir here when I say that I think security of the cyber-physical system is a topic of paramount importance. If you look at the NIST guidelines, many of them for the smart grid are on security, as a matter of fact. A science for security of CPS does not exist. It needs to be developed. I think we are scratching the surface through this example. I hope that by poking the interest and the curiosity of people, something will emerge. But I think this needs the work and the interest of a community, not just of a few people. And the last point is that I think security, cybersecurity, as we know it, needs to be integrated with system theory and system knowledge, which means for the security companies that are out there, start hiring control people. That's my final message. I would like to thank you very much for having me and for participating in this talk. Let me acknowledge my student Yilin Mo, my collaborator Le Xie, and the support of several organizations who have been supporting me through this effort. Thank you.
Do you have questions from people off-site? Okay, so we can throw it open to questions in this room.
Yeah.
I have a very simple question. The first attack which you showed, replay attack, right? If I'm an attacker and I know that you can detect this kind of intrusion in the system, what if by purpose I'm generating disturbance to the system and you're detecting all the time something and you have all these false positives? Wouldn't be this a problem, or?
So, I mean, you could do several things, right? First of all, you could choose to use this technique intermittently, right? So when you don't, and the attacker introduces a perturbation, you measure it, right? And that would not absolutely say that there's an attack, but there is a problem, right? That's one thing that you could do, right? For instance, the other thing, which is more brute force, is put a perturbation which is higher, but you don't want to do that, probably, right? So, I think this is what I presented. What I want to make clear, what I presented is a countermeasure. Okay, has no claim of optimality, and the reason why I presented is because I think architecturally gives this idea of authenticating cyber components via the physics of the system, which I think it's an interesting concept. But for instance, if you wanted to approach the system in an optimal way, you could design your gains for the controller and the observer so that you make that matrix A unstable, for instance, by stabilizing also the system, of course, which is not clear. So it's a constrained optimal control problem.
Bruno, when we get to large-scale systems, your A matrix is very large. I guess as long as it's not time-varying, you can compute all the eigenvalues, eigenvectors. But let's assume we're going to put in time dependence. Can you foresee that this can be done in a tractable way?
So when you go large scale, I think first of all, you go into the realm of, you don't have the luxury of collecting all data and computing just one control input. So you have to move into a more of distributed realm. And we have some work on that. The tools that I'm borrowing from system and control theory there are structure linear system, for instance, where through that, which have been used extensively in the fault detection literature. Here, Krista Dikostis was doing work on this field. So you can use some of these techniques to identify whether subsystems are performing maliciously, or maliciously are not performing according to the protocol. Yeah.
Improperly.
Improperly. So you break the system into smaller chunks, and there are results, I think, or machinery. Results not too many, but I think I'm confident there's machinery to do this. When you go into nonlinear systems and time-varying system, all bets are off, because these are difficult systems to analyze just from a control perspective, notwithstanding security. So you will have to do approximations, but people and control people have been living with linear approximations of control systems for the past 30, 40 years. If you look in the industry, rarely people use nonlinear controller. So what you could do is just take snapshots, right? If you can do time scale separations, for instance, and for a short time you can consider the system time invariant. These are the engineering approximations that I would do. From a scientific perspective, I suspect it's difficult to be able to say things conclusively in this manner. Yep.
So you were saying that there's a situation with .NET, but that doesn't happen every day. But also when you introduce disturbances into a control, but that might happen every day or every minute, because whenever we just steady state, you're going to disturb it. So now the question is, now apparently if there is no attack for a year, so you are going to subject to a huge amount of loss of performances, and how you account for that. And if I do it in a randomized way, it's very likely for me to miss the attack, and how you're going to compensate for that.
Yeah, it's a very good question, very good point. Yeah, so the question said, if the likelihood of your attack is very low, why should I perturb the system every 2 minutes when an attack is going to happen every 10 years, right? Yeah. I don't know how you would do it. That depends on the granularity of the attack and how fast you need to respond to it, for instance, right? If you have to respond to an attack you have, I don't know, an hour to respond to an attack, then you can do it every hour. But this is more of a risk management question, right? And so you have to assess the risk and the cost of the damage versus the cost of actually using this. And again, there might be more efficient ways of countering an attack. You could use dual strategies, for instance. I'm not saying that you have to use, and actually in engineering, what will happen, there will be a combination of things. Like there's all this software, I was speaking this morning also, software attestation schemes, where you go and ping the component directly to see whether it is compromised or not. So you could use a combination of different techniques, right? That maybe some are less accurate, but also less costly. And when you raise an alarm, then you use more powerful techniques, like like waking up Big Brother in some sense, right? You have very expensive sensors and very cheap ones. When the cheap one tells you if there is something wrong, then you use the very accurate ones to see if there is actually something wrong. I think there could be engineering. These things can be engineered.
Any other questions? Bruno, thank you very much. A very interesting discussion. I think you've given us a lot of ideas and a lot of things to think about. So thanks very much for coming here.
Thank you.
And the rest of you guys, tune in next month for the next for the net broadcast from this campus, still from Urbana. Thank you.
Thank you.